On August 6, 2025, the James Webb Space Telescope locked onto something moving through our solar system and captured the clearest, most chemically detailed reading of an interstellar comet human beings have ever produced. Not a blurry dot, not an ambiguous smear of light, a full spectral portrait, a direct readout of the chemistry of an object from another star system. The scientists who received that data used a word that almost never shows up in peer-reviewed planetary science: extreme. The numbers were so far outside anything ever measured in a solar system comet that the team spent months rechecking their own analysis before they trusted it enough to submit it. This video is about what Webb actually found, why the chemistry of this ancient visitor is forcing a genuine rethink of what planet-forming disks look like around other stars, and why the observation campaign that followed it became the most comprehensive scientific engagement with an interstellar object in history. Subscribe and hit the bell before this video ends, because 3I/ATLAS is gone from the solar system now, but the papers are still coming, and the next result could change the picture again. To understand why Webb's data was so surprising, you first need to understand what 3I/ATLAS actually is, and how unusual the opportunity to study it really was. Interstellar objects. Bodies that formed around another star and were later ejected into the galaxy to drift between stars, were purely theoretical until 2017. Astronomers had long argued, on solid statistical grounds, that interstellar space should be full of them. When a solar system forms, not all the material that starts the process ends up locked into planets. Comets and planetesimals in the outer disk get gravitationally scattered by giant planets, and a meaningful fraction of them get flung outward fast enough to escape their parent star's gravity entirely. They become free-floating wanderers, carrying the chemical fingerprint of wherever they formed, drifting through the galaxy for as long as it takes to randomly cross paths with another star system. For decades, this entire population was invisible to us, dark, cold, and scattered across an amount of space so vast that any given cubic astronomical unit is essentially empty. The only time one becomes visible is when it happens to pass close enough to a star to warm up, sublimate its ices, and grow a coma and tail bright enough for telescopes to catch. In 2017, the Pan-STARRS telescope in Hawaii caught the first confirmed interstellar object ever, 1I/Oumuamua. It was already outbound when discovered, moving too fast to intercept, and showed no coma or tail despite repeated attempts to find one. Its strangely elongated shape and unexplained non-gravitational acceleration sparked scientific debate that has never been fully resolved. In 2019, 2I/BORISOV arrived, clearly comet-like, with an active coma, the first confirmed interstellar comet. Its chemistry was studied in detail and found broadly consistent with solar system comets, with some differences. Then, on July 1, 2025, the ATLAS Survey Telescope in Chile caught the third, 3I/ATLAS, moving at roughly 250,000 kilometers per hour relative to the Sun on a hyperbolic path. The mathematical signature of something that didn't form here and isn't gravitationally bound to our star. It was already actively outgassing at a distance where most solar system comets are still dormant. David Jewett at UCLA, who confirmed its interstellar nature within days using the Nordic Optical Telescope, described it plainly, clearly active, growing a coma from the moment it was detectable. Unlike Oumuamua, and more chemically evolved than Borisov, 3I/ATLAS was, from the very beginning, a genuinely rich target. Arriving close enough, and at the right time of year, for Webb, Hubble, and an entire fleet of other observatories to study it before, during, and after its closest approach to the Sun in late October 2025. On August 6, 2025, Webb used its near-infrared spectrograph, NIRSPEC, to capture a spectral image of 3I/ATLAS while the comet sat about 272 million kilometers from Earth and roughly 3.3 astronomical units from the Sun, about the distance where Jupiter orbits. At that range, most solar system comets are only beginning to stir, still too cold for water ice to sublimate efficiently. 3I/ATLAS was already generating a substantial coma, Webb's spectrograph spread the comet's light across a range of infrared wavelengths from 0.6 to 5.3 micrometers and measured exactly which wavelengths were being absorbed or emitted, producing a chemical fingerprint as specific as a barcode. It's the same transmission spectroscopy technique Webb uses to read the atmospheres of exoplanets, now aimed at a body moving through our own solar system at interstellar speed. A team at NASA's Goddard Space Flight Center, led by Martin Cordner, processed the data, and what came back was a coma dominated by carbon dioxide, not water. Carbon dioxide, the same molecule that makes dry ice, sublimates at far lower temperatures than water ice, meaning it can stay active much farther from the sun. The ratio of carbon dioxide to water in 3I/ATLS's coma came out at roughly 7.6 to 1, about 8 times higher than any solar system comet ever measured, and several standard deviations above the established trend. That's not a marginal difference. Across decades of observing solar system comets, the range of CO2 to water ratios varies, but this result sits so far outside that entire range that it represents a step change, not a variation. It means the relative abundance of these two compounds in 3I/ATLAS is different enough from everything ever measured in our own solar system that it points directly to formation under fundamentally different conditions. The full molecular inventory Webb detected in the coma included water vapor, carbon monoxide, water ice, dust, and a tentative detection of carbonyl sulfide. Each of these species sublimates at a specific temperature, which corresponds to a specific distance from a star, which corresponds to a specific region within a protoplanetary disk. The ratios in which they're present are effectively a direct record of where, and under what temperature conditions, the material that became 3I/ATLS originally condensed. In protoplanetary disks, different volatile compounds freeze out of the surrounding gas at different distances from the central star. A series of frost lines, each one marking the boundary inside, which a given compound is too warm to remain ice, and outside which it can condense. Carbon dioxide's frost line sits significantly farther from a star than water's. A comet built primarily from carbon dioxide ice formed in the cold outer reaches of its protoplanetary disk, under conditions very different from those that built the water ice-dominated comets in our own solar system. The Nature paper Cordner's team eventually published put more numbers behind that picture. The methane to water ratio in 3I/ATLAS came out roughly 11 times higher than any previously measured solar system object. The deuterium to hydrogen ratio in its water, deuterium being the heavier isotope of hydrogen, measured at approximately 0.98%, about 30 times higher than the roughly 0.033% typical of solar system comets. Every one of these numbers, taken together with the carbon dioxide dominance, points in the same direction. A formation environment far colder and at a different stage of galactic chemical history than anything that built the comets in our own Oort cloud and Kuiper belt. This is where the story turns genuinely remarkable. There's a well-established relationship in galactic astronomy between a stellar population's age and how fast its stars tend to move relative to the local standard of rest, the average motion of stars in our part of the galaxy. Over billions of years, gravitational interactions with molecular clouds, spiral arms, and other mass concentrations gradually scatter stars in velocity space, so older populations end up moving faster, on average, than younger ones. By measuring an object's velocity relative to that local standard, astronomers can make a statistical estimate of its age. 3I/ATLAS was moving at more than 200,000 kilometers per hour, roughly 2.2 times the velocity of 2I/BORISOV. Astor Taylor and Darrell Seligman at the University of Michigan and Michigan State University used that velocity to estimate its age at somewhere between 3 and 11 billion years. Then Cordner's team took it further, analyzing the ratio of carbon-12 to carbon-13 isotopes in the comet's coma, measured in compounds like carbon monoxide, carbon dioxide, and organic molecules including methanol, formaldehyde, and methane. They found far more carbon-12 relative to carbon-13 than anything seen in our solar system, in nearby planet-forming disks around other stars, or in local molecular clouds. Combined with the deuterium enrichment, That isotopic evidence pushed the age estimate to somewhere between 10 and 12 billion years old. Our solar system is 4.6 billion years old. Our sun hasn't yet reached the midpoint of its expected lifespan. 3I/ATLAS formed somewhere between 10 and 12 billion years ago, when the universe itself was only about 1.8 to 3.8 billion years old, a small fraction of its current age of roughly 13.8 billion years. Whatever star it originally formed around has almost certainly finished its entire life cycle and died sometime in the billions of years since this comet was cast out into the galaxy. Matthew Hopkins and his team at the Center for Astronomy and Astrophysics at the Technical University of Berlin traced 3I/ATLAS's path backward using the Gaia satellite's catalog of nearly 2 billion stars, reconstructing the route it took through the galaxy to arrive at our solar system. Their analysis pointed toward the galaxy's thick disk. An older, kinematically distinct population of stars spread further above and below the galactic plane than the thin disk where our own sun resides, dominated by stars more than 10 billion years old, carrying the chemical signature of the galaxy's early history, before generations of stellar nucleosynthesis had enriched the interstellar medium with the heavier elements common today. That places 3I/ATLAS's origin in a genuinely ancient part of the galaxy, consistent with everything Webb's spectrum already suggested. A comet built around an old, metal-poor star in the galactic thick disk, from a protoplanetary disk whose basic chemistry was already different from ours, because the star itself formed from material that predated most of the heavy element enrichment already present by the time our own sun formed, 4.6 billion years ago. Webb's spectrum was only one piece of what became the most comprehensive multi-observatory campaign ever mounted on an interstellar object. While Webb read the chemistry of the gas, Hubble's ultraviolet and visible light instruments mapped the structure of the dust, revealing the coma's overall shape, dust grain sizes, mass loss rates, and the developing geometry of the tail as solar radiation pressure began pushing it outward. Together, the two datasets gave scientists something they'd never had for an interstellar object before: a complete portrait, gas and dust, chemistry and structure, describing the same body from two complementary angles at once. In late November 2025, JAXA's X-RISM X-ray satellite carried out a targeted observation and reported a genuinely new kind of result: a faint, preliminary X-ray signal associated with 3I/ATLAS, extending roughly 400,000 kilometers from the nucleus, a scale larger than the average Earth-Moon distance. Neither Oumuamua nor Borisov had ever produced a detectable X-ray signal despite attempts, if the emission is confirmed as genuinely cometary. JAXA's own team has been careful to note that instrumental effects need to be ruled out first. It would point to charge exchange between the outgassing coma and the charged particles of the solar wind, and would confirm that 3I/ATLAS's outgassing was extraordinary compared to its two predecessors. NASA's SPX mission caught the comet in December 2025 as it began its outbound journey after perihelion, in what SPASRX scientists described as a full-on eruption. Water emissions surged roughly 40 times over baseline levels in the weeks following closest approach, as the sun's heat finally penetrated the comet's insulating outer layers and reached deep interior ice that had been preserved, undisturbed, for billions of years in interstellar cold. The comet's rotation shifted measurably during that outburst, too, its spin period dropping from about 16.2 hours before perihelion to roughly 7.1 hours after, more than twice as fast as asymmetric jets of escaping gas acted like small rocket engines, gradually torquing the nucleus. Two spacecraft already en route to Jupiter got pulled into the effort as well. NASA's Europa Clipper, on its way to investigate the ocean beneath Europa's ice, was diverted from cruise operations in early November 2025 to spend hours imaging the comet. A spacecraft reprogrammed mid-mission to observe something nobody knew existed when it launched. Its ultraviolet instrument detected hydrogen and oxygen in the coma, the telltale signature of water ice sublimation, along with faint dust structures in the developing tail. ESA's JWST spacecraft observed the comet around the same window from a similar distance, and because its main antenna was doubling as a heat shield at the time, the full dataset didn't reach Earth until months later. including a sequence of images from its navigation camera, an instrument built only to track star positions for orientation that ended up capturing 3I/ATLAS moving through space with its coma and twin tails clearly visible. Right place, right time, doing a job it was never designed for. Together, the two spacecraft delivered something genuinely new. Simultaneous views of both the day side and night side of an interstellar comet's coma from two different vantage points at the same moment. One of the most precisely determined physical measurements of 3I/ATLAS came from a geometric accident in early 2026. On January 22, 2026, the comet passed within about 0.69 degrees of the Earth-Sun axis, the imaginary line running from Earth straight through the center of the Sun. That alignment placed the Sun almost directly behind Earth relative to the comet, eliminating the shadows normally cast by dust particles in the coma and briefly boosting its apparent brightness by roughly 20% through constructive interference of reflected sunlight. Hubble used that brief window to do something it couldn't manage precisely back in August 2025. Isolate the solid nucleus from the surrounding coma clearly enough to measure its size directly. The result put the nucleus at a radius of roughly 1.3 kilometers, a diameter of about 2.6 kilometers toward the smaller end of earlier estimates. Combined with the comet's extraordinary outgassing rates, that modest size suggests most of the nucleus's surface is actively contributing volatile material, rather than just a handful of isolated active patches. The same alignment revealed the structure of the comet's jets in remarkable detail. By filtering out the coma's symmetric glow, the Hubble team identified 4 distinct jets, one prominent sunward jet tracked for months, and 3 smaller jets spaced at roughly 120-degree intervals around that sunward axis. The near-perfect symmetry of those 3 smaller jets drew significant attention. Spacing that precise is unlikely to be random. The most plausible explanation is that they originate from compositionally or structurally distinct regions of the nucleus, positioned at those intervals relative to the rotation axis. A kind of geological fingerprint reflecting how the nucleus was originally assembled in its protoplanetary disk, billions of years ago. On March 16, 2026, 3I/ATLAS passed within about 53.6 million kilometers of Jupiter, close enough to enter the giant planet's Hill sphere, the region where Jupiter's gravity outweighs the Sun's for a passing object. The resulting gravitational deflection amounted to just a few meters per second of velocity change. Tiny in absolute terms, but almost certainly the most significant gravitational interaction this comet has experienced since whatever ejection event flung it out of its parent star system, potentially billions of years ago. By the time 3I/ALAS rounded the Sun and began heading back out of the solar system, roughly 500 papers and studies had already been published about this single visitor. More combined than had been produced for Oumuamua and Borisov together, and over a much shorter observation window. Part of that is simple accessibility. 3I/ATLAS arrived at an angle and time of year that allowed extended observation over many months. Part of it is that the observational infrastructure available in 2025 and 2026 was simply more capable than what existed in 2017 or 2019. Webb didn't even exist during Oumuamua's passage, and the infrared spectral portrait it produced of 3I/ATLAS would have been technologically impossible 8 years earlier. And part of it is that 3I/ATLAS simply turned out to be more chemically interesting than either predecessor, in ways researchers are still working through. The methane to water ratio 11 times higher than any solar system object, the deuterium to hydrogen ratio 30 times higher, the carbon dioxide dominance 8 times beyond the previous maximum, the first still preliminary X-ray signal ever associated with an interstellar object, the first detailed infrared coma spectrum of an interstellar comet, the first direct nucleus size measurement for one of these visitors. Every one of the major chemical measurements, the CO2 to water ratio, the methane to water ratio, the deuterium to hydrogen ratio, the carbon isotope signature, lands outside the range established by decades of observing solar system comets. No single measurement alone would be conclusive. All of them together point toward the same conclusion: an ancient, cold origin around an old star, somewhere in the galaxy's thick disk. That's the picture laid out in the Nature paper published on June 22, 2026. So what does 3I/ATLAS actually mean for how we understand the universe? It means we now have real chemical measurements from a real object, confirming that the range of protoplanetary disk chemistry across the galaxy is genuinely wider than our own solar system alone could ever reveal. Our comets are one data point. The chemical residue of our own solar system's formation, 3I/ATLAS, is a second data point from a completely different environment. Colder, more carbon dioxide rich, more methane rich, more deuterium enriched, built around a star whose disk simply didn't share the same composition as the one that built our sun 4.6 billion years ago. The galaxy is chemically diverse. Protoplanetary disks around other stars don't all look like ours. The comets those disks produce don't all carry the same volatile inventory. And when one of those comets gets ejected and drifts through the galaxy for billions of years before happening to cross our path, it carries that chemical diversity with it. A message from a distant, long-gone system, readable only by the right instrument if that instrument happens to be pointed at the right patch of sky at the right time. James Webb was. The observation from August 6th, 2025 produced a dataset that will be analyzed for years, and the papers building on it are still coming. The Vera Rubin Observatory is now fully operational, scanning the entire southern sky every few nights with a sensitivity that let it catch 3I/ATLAS in its own science validation data 10 days before the object's official discovery date. Whatever the next interstellar visitor turns out to be, it will likely be found earlier, tracked longer, and studied with everything this comet just taught scientists about what to look for and why it matters. 3I/ATLAS came from somewhere between 10 and 12 billion years away. It carried chemistry nobody had ever measured before, and for about a year, it let the most powerful telescope humanity has ever put in space read exactly what was inside it. What Webb found was surprising, and science, at its best, is exactly that. If stories like this, grounded in real, published research rather than exaggerated headlines, are what you want more of, subscribe and turn on the bell. The 3I/ATLAS papers are still coming in, the UICE data is still being processed, and every major result from this extraordinary ancient visitor will be covered here with the same sourced, careful approach you just heard. Thanks for watching, and I'll see you in the next one.